All right, hello everyone, and welcome to Studio 6 Review. This is one of the more difficult weeks in the class. We're covering recursion this week. I think recursion is one of those topics that kind of grows on you, although I talked to several people in Studio who said they like recursion just fine. Thought that was great. In this studio, we actually have you compare recursion with iteration. So iteration and recursion, remember, are two different ways of performing repetition in our code. Iteration uses a series of loops, for loops or while loops to do repetition, whereas recursion is just going to use repetitive method calls, a method that calls itself to perform that repetition. So we're going to compare and contrast those two approaches today by having you look at some methods done with loops and some methods using recursion. So let's go ahead and start by taking a peek at geometric sum. You're given the geometric sum, the iterative version of the geometric sum method. You can see here how it works. It passes all of the tests. That's good. So it's computing the sum of the value 1 plus 1 over n to the first power plus 1 over n to the second power, etc., 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 all the way up to some given value. Well, n was negative 4 choice, but here, this is a better explanation than what I just gave. 1 over 2 to the 1, 1 over 2 to the 2, 1 over 2 to the third power, 1 over 2 to the fourth power, all the way up until we get 2 to the nth power. And so we need to determine how to switch this into a recursive method and write a recursive formulation of geometric sum. So in order to do that, we need to consider two parts, right? What is the base case? When do we stop? And what is the recursive step? How do we keep going while still progressing towards the base case? And so typically we would write an if statement where we would use the first part of the if statement for the base case and the second part for the recursive step. I think that'll work pretty well for us here. So when do we stop? If we look at the way that this is computed, n actually determines how far we go. So n is going to be changing. If n is 4, then we stop here. If n is 8, then we'd stop after that many terms. But we always compute the first terms, right? So I think working our way towards the left is the way to think about this. The last term is always going to be 1 over 2 to the first power. So we can reflect that by having that be our base case. If n is 1, then we know what our answer is. So if n is equal to 1, then we know what our value is. It's going to be 1/2. Otherwise, we have some work to do. Otherwise, we need to compute the value of whatever our term is, and then add that to the rest of the series. And that's our recursive substructure. So the geometric sum of 4 is equal to this term plus the geometric sum of 3, represented by these three terms. The geometric sum of 3 is represented by this term plus the geometric sum of 2. So if we wish to express that in code, the geometric sum of n is equal to 1 divided by math.pow 2 to the nth power plus the geometric sum of n minus 1. This will be our return value for all other values of n that aren't 1. All right, let's run our methods and run our tests rather, and see if we've made any progress towards getting this computed. It looks like I see a lot of green here, but I also see there's an error for when the value is 0. Okay, so maybe we didn't stop soon enough. Maybe we needed to, or maybe we stopped too soon. Maybe n equals to 0 is our base case, and we should return 0. Let's switch up the base case a little bit and rerun our tests, and see that now all of the geometric sum tests are passing. Okay, so this is a pretty simple recursive method. I actually want to work through one of these with you in the debugger, though, just to get you some more practice with how we actually run these recursive methods. So what I'm going to do is I'm going to set a breakpoint in the test. Once we get to a value of n that we care about, we can use the debugger to step through that code. So let's go ahead and start this up in the debugger. I set a breakpoint here in the test. The value of n that we're using right now is 0, so I'm actually going to continue until we get a more interesting value of n. Now we've got our value of n, which is 5. All right, that's good. I'm going to go ahead and step into this. Let's keep stepping in. Here we go. Oh, this is our iterative version. Well, that's not what we want. We want the whoops. All right. I got off track. I clicked into the iterative version of the tests, apparently. Or it ran the iterative version of the test first, is what happened. And I wanted to do a recursive version, not the iterative version, so I'm going to try a different tack with debugging, which is fine. I'm going to set a breakpoint right here in my recursive method instead, and I'm going to turn that other breakpoint off once I can find it, because that one was not working for me. So let's go back here. I think it was line 32. Yeah, turn this one off. And let's try that over again. Let's see if we can hit our breakpoint. All right, great. Now we see the case where n is equal to 0. And that's our base case, so that's easy. Let's continue on until we see some more exciting values for n. Here's one for n is equal to 3. All right. 3 is not our base case, so we're going to skip that, and we're going to compute 1 over 2 to the third power. But then we're also going to call geometric sum of n minus 1, which is the geometric sum of 2. So if I step into this, we take a look, we see that we now have 2 different versions of geometric sum up here, right? I can proceed along, see that I still haven't hit my base case, n is equal to 2. So if I step in, I'm going to compute this term and then call the recursive case for geometric sum of 1. Still not my base case, so I compute one more term. That's our 3 terms. For n is equal to 3, n is equal to 2, n is equal to 1. So we've computed all 3 terms, and now I finally hit my base case, but we're not done yet. Remember, when we hit the base case, we're actually only halfway there. We have to traverse our way all the way back up. So this base case is going to return a value of 0 that gets passed up to the recursive method call for n is equal to 1 and adds that to the term that was computed. So that should be 1/2, right? So that value gets returned, and then we add that to the term that gets computed here, 1 over 2 to the 3. And then we keep doing that all the way back up until we hit our original value, which gives us a geometric sum of 0.875 for n is equal to 3. Okay, going to move along and start in on the next problem now. Recursive drawing. So this is actually an example of a divide and conquer problem. When you're faced with the divide and conquer problem, or how I know it's a divide and conquer problem, is because I actually see the same pattern appearing here multiple times. So once I draw this big circle, I see 4 more circles, right? Actually, I think down here it explains it a little bit more detailed, right? Once I draw this circle, I'm going to draw 4 more circles. And then for each of those 4 circles, I'm going to draw 4 more circles. And then for each of those 4 circles, I'm going to draw 4 more until we hit our base case. So divide and conquer problems like this are going to have one recursive call for each of the smaller problems. So I actually expect to see 4 recursive calls as part of this method. Let's go ahead and take a peek and see if we can start working on the circles problem here. Here we go, circles upon circles all the way down here at the bottom. It gives us the center point, it gives us the radius, and it gives us the minimum drawing threshold. This is what we're going to use for our base case. So if the given radius that we're being told to draw is less than the radius minimum drawing threshold, then we're just going to stop. We're going to return. Ugh, I can't type. There we go. We're just going to return. Otherwise, this is where we're going to do our drawing / dividing and conquering. We're going to draw the circle. We want to use the radius here, not the minimum radius, but just the regular old radius. And then we're going to call the method 4 times. So we need to figure out what the new values are for the x center, the y center, and the radius in each of these 4 directions. So I've just drawn this big circle. I have this value and the radius. So how do I get from here to here? Well, I'm going to move to the left. So I'm going to write a recursive call that moves us to the left. It's going to be called circles upon circles. We're going to move to the left by shifting our x center to the left by the radius. The y center will remain unchanged because it didn't move up or down, it just moved to the left. And then we're going to divide the radius by 3 to make the next circle look even smaller. And we actually need to pass the radius minimum drawing threshold as well so that we can check our base case. And if we are ready to start testing, we can actually run this circles demo app and see if we have any circles on the screen. There we see, all right, we got 1 circle. Let's continue on to the next. And since I've only done 1 of the 4, I don't see all 4 circles yet. I just see the one on the left. But as I keep adding calls, we'll start to see more and more circles appear on the diagram. So let's redo this, and we'll do the circle going to the right next by adding the radius to the x-coordinate. I'll run that demo app again and see that now that we have 2 recursive calls, one going to the left and one going to the right, I see two circles on either side. And if I actually keep going, it'll keep doing the circles to the left and the right, but it's not doing any of the ones going up or down. We haven't written those recursive calls yet. It is working though. All right, so let's do the north-south ones by adding and subtracting the radius to the y-coordinate. This should take us up. I can run this and verify. There we go. Now I have 3 circles. And then if I copy this one more time, let's flip the sign on this radius to move us downwards. We can see that all 4 circles are being drawn in all 4 directions, and it's taking us 1 step down, right? It's cool. Oops. Expected image not available. Well, it kept working. Looked like it kept working. Again, just to kind of review, this is a divide and conquer problem. I can tell that because I see the same recursive pattern appearing more than one time. So I know once I see that recursive pattern appearing in 4 different directions, then I'm going to have 4 recursive calls. If I only had that pattern repeating 3 times, then I would only have 3 recursive calls. So divide and conquer problems are always going to have that recursive call structure match up to how many times the recursive pattern appears in the problem that we're trying to solve. Okay, let's move on to the next one. We're trying to reverse an array. So I'm going to do a recursive problem using an array now. So if I come back here, if we take a look at the way that we reverse an array using iteration, notice that it creates a copy of the array and then reverses it. So it's doing that by iterating through everything and then swapping the values. We're actually copying the values over from the mirror point and then also from the regular index. It's actually only iterating through half of the array. You can see it's only going through length divided by 2 because it can copy 2 values at once. So it can copy the mirrored index as well as the regular index. And I'm going to try and write recursive code that can mimic this. Also notice there's some stuff up here that doesn't occur inside the loop. It only occurs once. Also notice that this loop is keeping track of an index variable for us, which is going to be tricky if we're using recursion because methods have local scope, meaning I can't see those variables outside of the methods. But since we're repeating our method calls many times due to recursion, we need to see this loop variable. We need to know which part of the array we're at. All right, let's see if we can do it. I'm going to go ahead and start piecing together this reversed method. I think in order to pull this off, we're going to need a helper method. And there's 2 reasons that make me say that. One is that I have some stuff that's not being repeated. So that's one thing that helper methods are used for. Anytime I have some code that needs to be repeated and some code that's not repeated, we can use a helper method. The helper method is going to be the one that replicates the repetition. It takes care of this part of the code. Any of the code that's not being repeated is going to go in the non-helper method. So I'm actually going to start just by copying this chunk of code right over directly. Why not? There's nothing wrong with that. And then we're going to create a helper method. The nice thing about this is that we can add more parameters. So I may want to add in this new array that I've made. So this is the source array that I don't want to modify. And then I have my destination array as well. And then I also, to keep track of where I'm at in these arrays, I'm going to include a loop variable I. So this is the second thing that helper methods are useful for. They help us isolate the recursion. They help us isolate the repetitive code from the non-repetitive code. But they also allow us to add more parameters to assist with the recursive execution, which again might be necessary. Again, just remember that in the iterative version we had the loop managing the loop variable for us, but using recursion we're going to use the parameter to manage the loop variable for us. And so what needs to happen here, we're actually going to call our helper method. Let me change the name of this to reversed helper. That's our helper method. And we need to specify what the values are. So there's our input array, there's our reversed array, and we need to set the initial value for I, which is probably just going to be 0. Get that out of there. What are we unhappy about now? Are we missing a bracket? Why does it say that we're missing a bracket here? Oh, we are missing a bracket for our if statement. So if the array length is bigger than 0, then we're going to return that. Otherwise, what does it do if the in the original, if the, oh, it just returns, gotcha. Okay. There we go. Try to mimic the original as much as possible. Down here, we're going to try and recreate the for loop. So the for loop goes from 0 up to and equal to array length divided by 2. So this is our stopping point of our for loop. This is going to become our base case. When the index is greater than the array length over 2, we're going to tell our recursive method to stop. So that'll become our base case. We can just return our reversed array at this point. It should be done. Otherwise, we actually have to do the reversing. So this is going to involve copying 2 values, just like we did here. In fact, I'm just going to go ahead and use this code directly. I don't see any reason why I shouldn't. It does exactly what I needed to do in this case. We do have the problem of, that's called I now. What's last index referring to? Last index is array.length minus 1. Okay, so that's going to be, there we go. Can do that. And then finally, we need to do our recursive call. So the way that this is going to recurse is by calling the reversed helper. The array and the reversed array are passing through unchanged, but I is going to go up by 1 to indicate that we have finished the position of I that we are currently on. And the next time we do our recursion, we're going to take a look at the next value and copy that next value over. Let's run the test, and then I also want to see if I can get this one into the debugger so we can take a peek and see. I believe geometric sum. Where is, to reversed. Here we go. Looks like we've passed all of our tests. But let me see if I can get in here and examine one of these tests to see what it looks like in more detail. Let's see. Start this up, run it in the debugger, and see if I can get into that. So that's our iterative test. I'm going to continue through all these iterative tests and see if I can get back to the oh, well, I passed them. Sorry about that. In fact, I should only be running the recursive tests. I think that's my fault for even trying to run the... Here, let me tell it to just run the recursive tests. There we go. All right. Now this should be running our recursive code, and let's find an interesting example that we can go through. Here's a good array, 1, 2, 3, 4, 5. I want to see how it's going to reverse this array, so I'm going to go ahead and step in and take a look at our recursive code. We are in the non-helper method right now. So this is the non-helper method. This is going to do all the stuff that only needs to happen once. So it's going to create the new copy of the array that we need. It's going to check the size of the array. And if it's big enough, then it'll go ahead and kick off. Oh, we actually don't need this line at all, do we? If it's big enough, it'll go ahead and kick off the recursion via our helper method. Otherwise, the answer is just our empty array. So let's go ahead and step into the recursive helper method. Again, remember, oops, I forgot to step into the recursive helper method. I clicked the step over button instead. Sorry about that. Just a second here to get back. Here we go. Step into. Let's do step into this time. Oh, now we're back on the iterative version again. I am just all over the place today. There we go. Let's get the bigger one. That looks good. Step into. It's recursive. And then finally, I'm going to click step into here so that we step into the recursive method. And now we're going to run through this. This, remember, is our helper method that includes additional parameters to help track the recursion. Our I variable has started out as 0. Our array is just our original array. And our reverse array is just empty. So it's waiting for values to be filled in. We haven't hit our base case yet. So it's going to copy 2 values per loop. So here we do the first one. There you can see the 5 coming in. Then we do the second one. There's the 1 coming in. And then it says, let's keep going. We still have more stuff that we need to do. Still haven't hit the base case. I is equal to 1 now. So we're going to do 2 more values this time. And if we take a peek at our array, we see the 5 and the 1 from last time. Now we get the 4 and the 2. So those are the ones that we pick up this time. But we're still not done yet. We're going to do one more level. Now the value of I is 2. The length of the array is 5. 5 divided by 2 gives us 2.5. So is I greater than, is 2 greater than 2? It is not, actually. So we're going to do one more recursion here. This time it's actually pointing at this, it's going to end up pointing at the same value in the middle. It's going to copy that 3 twice, which is a little bit of a redundancy. But you can see now that our reverse array is in fact complete. So we'll do one final step into this method. We see that I is now 3, which is greater than half the length of the array. We know that we're done. So we've hit our base case. The array is reversed. We can actually verify that by looking at the contents. And we'll simply pass that array all the way back up and verify the contents in the test. Okay. I believe we have one more recursive method to look at in this studio, which is called greatest common divisor. This is another example where we want you to take a look at the iterative version and then see if you can convert this into a recursive version. So let me go ahead and pull up the iterative version of greatest common divisor, which is right here. It uses a while loop, and while loops and recursion go pretty well together. So let's go ahead and see if we can start piecing this together. Actually ends up being pretty straightforward if you just follow the pattern, right? We actually give you the English expression here, which you can also use, right, to help you code this up. And so the method, here it is. We're going to put it right here. Our iterative method that says while q is not equal to 0, we're going to keep going. So if I want to use the same condition here, I can say if q is equal to 0, that's going to be our base case. This is going to be when we stop. What do we return when q is equal to 0? Let's work through this and see. When q is 0, we return p. We just return p. Okay. Otherwise, we're going to do the stuff that is inside of this loop. We're going to compute a temp value and have that be equal to q. The new q is, well, actually, this temp value ends up going to p. So the new p is equal to q, and then q is equal to p mod q. We can actually do that just via the method call very directly by saying return GCD. Remember, p is now q, and q is equal to p modulus q. I believe that will actually do it. But let's run the tests and see. There we go. They all pass. All of the unit tests for this studio have now passed. Again, just to reiterate how I got here, I looked at the iterative method, and I saw that q was being stored to p via temp variable, and then q was being redefined as p mod q. So I just took those two variable assignments and I did them right here. When I call this method, this is the value that I want to be for p, so I just set that to be equal to q. And then this is the value that I want to be for q, so I set that to be p mod q. Remember, there's an implied assignment that happens when I plug these values in. They get assigned to p and q the next time the method is called, and the next time the method is called. So this is replicating the exact same behavior as the while loop. It's just using recursion, repeated method calls, to compute the greatest common divisor instead of using a loop to perform that repetition. All right, you've got some more recursive puzzles to work on this week. I think it's important to understand with every problem you approach whether you need a helper method or not, and then whether it's a divide or conquer problem. There are problems on the homework assignment that are going to use helper methods. Those most often, not always, but most often involve arrays. So that's a good clue that you might need a helper method. There's also a problem on the assignment that does involve the divide and conquer method. So pay attention to that. If you see the same recursive pattern appearing more than once, that's a clue that you're going to have to call the method more than one time to account for all the different patterns. All right, that's going to wrap it up for the studio. I hope you all have a great weekend and a great spring break.